paper. Next paper will be given by Ton KU on integration of borehole and seismic data into magnetotelluric inversion. Case study over the same, by the way, Kivitsa ultramatic intrusion, northern Finland. So we continue study the same deposit but using different technique. And Ton is a graduate student at the Curtis University in Australia, and I think this is a part of your thesis research, your PhD thesis research. You're welcome.
Okay. Thank you, and good morning, everyone. First, I would like to thank my co-author, Anton, my supervisor, and my colleague, Le. The main purpose of our talk today is two things. The first is how we include various information to constrain inversion to make the model more reliable. The second purpose is how we can build up the model that help the interpretation process easier than we using directly from the model of inversion. So I use the same dataset, Kivitsa dataset, to demonstrate our ideas. So the challenging here is complicated logical structures, and as you can see, the seismic data is not really good like in the sub-rock environment. So what can we do with this situation? Fortunately, we have a lot of borehole here with various types of data, and the distribution of resistivity in this area is quite nice and simple. Here you can see two peaks of the resistivity distribution. One related to the country rock, the other one related to the mineral or maybe carbon fly sediment rock. And the question is how we include a whole bunch of the borehole information here into the inversion of the empty data. To do so, in our routines, we use the fuzzy clustering to include borehole information into the inversion. So the question is, why is fuzzy clustering? The basic idea of using fuzzy clustering in the inversion is, in the fact, we usually divide the subsurface into rock units, and each rock unit we have different features. But the situation is boundary between the rock units usually unclear or fuzzy. So it's a fuzzy logic or fuzzy clustering applied in the geology. It's quite nice. In this figure, we can see the schematics of how we put the cell of geophysical model into rock units. We have a cell with many features, and each feature we have a different contribution in the way we put the cell in the cluster. It depends on uncertainty of the feature. It depends on the purpose of the clustering. More specifically, we use a fuzzy C-mean clustering in our process. So fuzzy C-mean clustering is an unsupervised learning algorithm that separates the items into clusters. And each item can belong to many clusters, but with different membership degree. In this view, membership degree can be likelihood or maybe probability of setting up the items in the clusters. In the point of view inversion, for example, we have a model including many samples of the model, we want to divide the model into cluster. We have the central value and membership degree. And in central value points of view, we can relate to the spatial-physical domain, and membership degree, we can relate to the spatial domain. That means if we can integrate fuzzy C-mean into the inversion process, we can constrain both structure and spatial-physical in the inversion. To do that, we add each the constraint term fuzzy C-mean clustering into the conventional objective function of inversion, including midfits and structure terms. Here we have one synthetic example, the true model. The true model here, we have 4 objects and the background. And we run inversion, we got the inversion result here. Below panel, we have a distribution of the inverted model, black bar, and the red is the true model. In terms of the smoothness constraint, we can see we have an artifact here, here, and here. And the boundary of the objects is unclear or smooth smear. And distribution of the resistivity, you can see it's ranging from smallest to the highest of the real resistivity of the model. Move on to the inversion with FCM constraint. We can divide the model into some cluster, and we can see that even here the result is still have some artifact, but in the basement this artifact is removed. And the distribution of resistivity is closer to the true model compared to the smoothness constraint only. In the third case here, we assume that if we know the information of the cellular objects here, we can divide the section into 2 medias. One related to the object, the other the background of the model. So we can include this feature together with the resistivity of the models into the cluster process, and we can get this result. The inverted model, it nicely fits with the true model, and the distribution of resistivity is closer to the real model. So in this case, in this synthetic example, we can learn 2 things. First, we can include many types of information into inversion process. And another thing is very important is if we know the shallow part of the section, we can improve the inverted result in the deeper part. Here we can see. So this is very common in the exploration because we usually have a shallow information, but the target is in the deeper part. So move on to the real application. We also use the KVSA dataset. And thank to Mahamir to introduce about this area here. We have 3D, sorry. We have 3D seismic and empty line here. And we have around 900 holes in which we have around 70 holes with the resistivity measurement. So this is the distribution of the resistivity. Sorry. Oh. Sorry. It's a bit confusing. Sorry. I want to back.
You want to go back?
Yeah.
This is back.
Oh,
Forward.
all right.
This is for later.
All right, thank you. Sorry. So we have the distribution of resistivity from 70 hosts. Definitely, we can include this information into the petrophysical constraint in the inversion process. But the question is, how about another borehole features from the other borehole without resistivity measurement? We have many holes, so we can include this information into the inversion process. To do so, we take another step of the analyzing the data. We use the elemental analyzing data to correlate with the resistivity, but unfortunately, we can see that here, the correlation between resistivity and outside data is not really high. The coefficient less than 0.5. So we maybe get some issue if we directly apply the assay data into the inversion process. So we use the assay data, normalize. Here we can see we get the nicely correlation between resistivity and nickel and copper, for example. So we put this information into clustering process. We decide the sample borehole and project into the empty section. So how to project? We assume that each cell of the empty mesh should be the same with the closest borehole sample with different level of certainties. The level of certainty can be calculated by the distance between the borehole sample to the mesh. Here, for example, we have a empty mesh here. We have a borehole around, and the winning sample should be the closest to the mesh. And here we can calculate the certainty and the projected cluster section from borehole information to the empty mesh. And then we put this information into the inversion, the same with the synthetic example, and we got the inverted result here. Here we compare the inverted result with the smoothness constraint from the modem code, and in this inverted model with only petrophysical constraint, and here we include petrophysical constraint and elemental information from boreholes. In the right hand side, we have comparison between inverted resistivity and the borehole from the central hole KV28. We see that the trend of the smoothness constraint inversion doesn't keep like our work compared to the resistivity of the borehole. And in here we can see some artifact here, and the consistent between the borehole resistivity and model is not good here. But in our work, we had consistent between the borehole and the inverted model, and here we remove the artifact here. For more detail in this result, we see that still have a conductive zone consistent with the borehole here, and you can see some consistent here and here. Thank you. The next is how we include seismic and empty together. Here we take the resistivity and acoustic impedance from the borehole. We cross plot here. And we use the fuzzy clustering to calculate the membership degree from 0 to 1. And the black shows the small membership degree, and the colorful area shows the high membership degree. So we see that we can divide the data into different units related to the resistivity and acoustic impedance. Apply the same with inverted model from seismic and empty. In the left-hand side here, we have the section of the acoustic impedance from seismic inversion. We don't have time to talk about the seismic inversion here, but we also do the same thing with the empty inversion in terms of exploiting the borehole information to have seismic inversion. So in this case, we have acoustic impedance from the seismic model by inversion. And here's the resistivity section from the empty inversion. And the rectangle here shows the position of the seismic. We put the seismic acoustic impedance and empty resistivity into the cluster process. We got the cluster section here with the 7 cluster, and we call it a pseudo lithological map. We can see that the cluster map or lithological pseudo lithological map is closer to the contact of geological interpretation process rather than using acoustic impedance or resistivity model. For example, here we can see that this zone is mainly related to the dunite, and here. And this part related to the olivine area. So if we can make the model become very simple formats of the image that can help the geologic interpretation easier than using the acoustic impedance model or resistivity model. So in conclusion, in our work, we use the fuzzy clustering as a platform to include prior information into the inversion, and the prior information can come from, for example, elemental information or physical information. The final product of the inversion is a cluster map or pseudo lithological map, can make the interpretation process much more easier than using the model of the physical distribution. I would like to acknowledge DAT CIC who support our work, and also would like to thank First Quantum Mineral and Validian company for the use of their data. We also would like to thank Lee from Korea who provide us the MT code, and thank EAGE and organizer for invitation. Here is some of my project partner and some references I will use in this presentation. Thank you for the attention.
Thank you very much. And we have time for questions.
I have 2 questions. The first is, how do you search the trade-off parameter beta and the gamma, right? Is there beta and gamma? And the second question is, you use the mod-EM inversion, and I see there is too much artifacts. So how many iterations did you use? Thank you.
Thank you for the questions. The first question is related to the regulation parameters. Actually, that's kind of the issue. Is I think it's very common in the inversion. We usually use a numerical experiment to decide how we can set up the parameters. In our work, we keep the constant parameter because I also test with the different strategy from the published paper, but I realize that when I keep it constant, it work stable and give the best results. For the second question related to the modem inversion, I'm sorry, I just the guy who work with 2D Lee code, the MATLAB code actually. My colleagues who work with the modem code, so I forgot to ask him how many iterations he used. So sorry. If you want to know, I can ask him and answer you later.
I maybe have some follow-up questions. How you select this constant value regularization parameter? You say use constant value, but how you select it?
Actually, I do experiment numerical method. At first I set up very big and reduce, and then I choose the best
so
one.
So you still select, so
Yeah,
you still
yeah.
change.
Yeah,
Okay.
yeah.
This is the point. Okay. Any other questions? I do here. Thank you again. Yeah.
Thank you.